All right, today we're implementing leak code 416, partition equals subset sum. My last video we solved this on the chalkboard. Now we're going to be implementing in actual code. All right, so I have this boilerplate and driver code here. All it is a class solution where it has one method, and here we're just calling that class in solution. We're making an instance of the class and then calling that function with the parameter of this array. Now remember what the problem is. It says we're given a non-empty array nums containing only positive integers, and the goal is we have to find if the array can be partitioned into two subsets such that the sum of both or all the elements in both subsets are equal. Right, so in this example right here, we're given 1, 5, 11, and 5, and it will be partitioned into 1, 5, 5. And then the other one will be 11, because 1 plus 5 plus 5 plus 1 and 11 are equal. So, the first step, what we did and when we talked about in the last video, is that we have to calculate the total sum of all the numbers in the nums array, and then divide that by 2 because we're trying to find two subsets. And that sum of the total divided by 2 will be what we're looking for when we're writing our backtracking function. And if we get that sum down to 0 evenly, we can return true. Hope it'll make more sense after I code it. So the first step is to make a integer total set equal to 0, and then for int I equals 0 if I is less than the integer version of the nums dot size, we'll just increment I, and then do total plus equals nums of I. Okay, so now since we have the total, what we can do is say if the total percent 2 does not equal 0. So if it's not even, we can return false right away, because we know if it's not even, we can't divide it evenly by 2, therefore we cannot make two subsets that are equal. So we can return false right off the bat. Now, if it is even, what we can do is create our sum. So our sum will equal our total divided by 2, and then we can just return our backtracking function. So our backtracking function will take in the parameters of nums. It will take in the sum. We're also going to add a DP array to add caching, so we don't create extra calculations that we don't need, hence the dynamic programming. And we're also going to need an index, but the index is going to start at 0. So I'm actually going to create this DP array, which is going to be a two-dimensional vector of integers. Call it DP with the size of the integer version of nums.size plus 1, because it's 0 index based, and just to be safe. And then vector of int with the size of the sum plus 1. So our dimensions of our two-dimensional array are the sum and the index of the array, which is how we're going to calculate where we are in the calculations. And we're going to initialize everything with all the numbers within the two-dimensional array are going to be initialized with the -1, because we can't store any -1 values anyway. So perfect. Now we can make our backtracking function. Passes in the single-dimensional array nums. I'm also going to give it the memory address, just in case we want to change anything inside of it, or change the state. We pass in our integer sum and our two-dimensional vector dp and our integer index. Okay, now we gotta figure out our base cases. So our base cases initially will be if the index is greater than or equal to the integer version of nums.size. Reason for that, because we don't want to get out of bounds. If we get out of bounds, we can return false right away. I'm returning 0, but 0 is equivalent to false in C++, and 1 is equivalent to true. However, one of our basic cases are going to be if the sum is equal to 0, and this is what we want. The goal is to get the sum equal to 0. If we can get the sum equal to 0 even once, that means it can work, because our total in this example, where we're given 1, 5, 11, and 5, the sum will be 22. So when we divide 22 in half, we're going to get 11. And if we can get 11 equal to 0, that means in the array we take out or initially 22, we take out 11, that means 11 has to be in there, which means we can divide it into two 11s, and that's what we want. And so if that happens, we can return 1 or true. And then if, probably one more base case is if the sum is less than 0, that means we went too far, and we don't have to make any more calculations because we don't want a negative number. So we can just return 0. Right, so, and now we can start implementing the dynamic programming part of this. So if the DP at the index sum equals -1, which means we have not calculated this spot on the two-dimensional array, we can start making that calculation. So we can just return the, just say we can just return the recursive function call, giving it our nums, our sum subtracted by the nums at the current index, because we have to make progress to start going down to 0 eventually. And then we can take the DP and the index +1, and we're plussing 1 to the index because this is a bounded. We can't reuse things. If this was like an unbounded knapsack problem, I wouldn't increment 1. But since we're using it, we move on, and that would be it. Or f of nums sum DP and index +1. Now, what does this mean? Now, this right here, remember when we created our decision tree? We created two paths in our decision tree, and that's what this represents within our code. This represents the path in which we use the current element that we're on, and then this right here is the path that we skip the current element that we're on. Because again, we have two choices, which is why the time complexity is 2 to the nth power without DP. With DP, it will take that exponential time complexity and turn it into a polynomial time complexity, and it will work against the test cases on LeetCode. But so that's what we're returning, and it's an OR statement because if you take two function calls that either can return true or false, the OR will return true if at least one of them are true. Okay. Else, which means we've already computed it, we can just move on. So if DP of the index sum is not equal to 1, which means we've already calculated that, we can just return f of nums, giving it the sum DP and then the index +1. Okay, and of course I forgot something very crucial. We have to give the memory address to the DP so we can actually update it. If we didn't do that, our DP array would have been completely useless. However, we also need to store these values that we're computing into the actual array. We haven't done that yet, so I'm going to say DP of the index at the sum will be equal to the result of this function right here. Right? Just like that. Perfect. All right, and I also have to store it on the other path as well. So DP of index sum will equal that. Cool. All right, so I believe this should work, but I do want to time our execution, so I'm going to include time.h right here, and then I'm just going to time how long this algorithm takes in milliseconds. So I'm going to create a start with a clock here before we start the function call, and then int e for the ending. We'll end the clock here after it's done, and then we can just see out the computed time in milliseconds. So the execution time will be a float, if I could spell it, float of e minus s, and then ms for milliseconds. Okay. I believe this should work, but let's see if we ran into any errors. Okay, no errors. Perfect. All right, so the execution time was 33 milliseconds. That looks pretty good, and we returned 1, which means true, which means it is possible to split this array into two subsets that are equal, and we know that is true because of this here. So what we can do is we can test it. So we can copy our solution, go into LeetCode, paste our solution here, and submit and run the code. See what happens. Right, cool. So it's faster than 48% of online submissions, and it uses, the memory storage isn't that good because we are using a call stack on our recursive calls. Going recursive is cost heavy in terms of space complexity, but I think the iterative way, I would have to check. I think the iterative way might use a little bit less space, but I think it might be a little bit slower. But the solution is good. I liked it. Yeah.